Okay, well, welcome back to our class on algorithms and data structure. We're winding down for the material that we'll be covering. We just went through an interesting chapter talking about the binary search tree implementation, and now we're going to be getting into a heap implementation. So why don't we just go directly into that? So just to begin out with, here are the things that we'll be talking about in this subject, this chapter. So we'll be giving a little bit of reprise about the ADT heap, which we talked about before. Then we'll talk about using an array to represent a heap, adding, removing an entry, adding an entry, removing the root, creating a heap, and doing a heap sort. So you may recall from chapter 24 that a heap is a complete binary tree whose nodes are ordered in a certain manner. When a binary tree is complete, you can use an array to represent it in an efficient and elegant way. The most common implementation of a heap uses an array, and that is the one we will describe in this chapter. As you saw in chapter 24, you can use a heap as an efficient implementation of the ADT priority queue. Later, this chapter will show you how to sort an array by using a heap. So just as a reminder, a reprise of the ADT heap. A heap is a complete binary tree whose nodes contain comparable objects. In a max heap, the object in each node is greater than or equal to the objects in the node's descendants. Segment 2433 provided the following interfaces for the heap. So here we get a chance to be seeing that. Note you can also have, may have heard the word heap used to refer to the collection of memory cells that are available for allocation to you through your program when the new operator executes. But that heap is not an instance of an ADT heap that we are discussing in this chapter. It would be covered, however, in a book about programming languages. So let's talk about it using an array to represent a heap. So representing a complete binary tree, we begin by using an array to represent a complete binary tree. Complete tree is full to its next to last level, and its leaves are on the last level are filled in from left to right. Thus, until we get to the last leaf, a complete tree has no holes. Suppose that we number the nodes in a complete binary tree in the order in which a level order traversal would visit them, beginning with 1. Figure 27(1a) shows such a tree numbered in this way. Now suppose that we place the results of the tree's level order traversal into a consecutive array locations beginning at index 1, as figure 27(1b) shows. This representation of the data in the tree enables us to implement any needed tree operation. We begin at index 1 instead of 0. We can simplify the implementation somewhat as we can see. So let's start looking at the class, the heap max heap, I'm sorry. In listing 27(1) that we're showing here, our class begins with the following data fields: an array of comparable heap entries, the index of the last entry in the array, and a constant for the default capacity of the heap. If last index is less than 1, the heap is empty, since we begin the heap at index 1. Two constructors are similar to constructors we have seen before in array-based implementations. We allocate one extra array location since we will not use the first one. The method getMax is empty, getSize, and clear have simple implementations that are shown in the listing. We consider that the methods add and remove max next. So we're just a little bit of high level, and you can see some of these details that we won't go over in detail, but you can look them over in the text or review these slides. So how about adding an entry? The basic algorithm, the algorithm to add an entry to a heap is not difficult. Recall that a max heap, the object in a node is greater than or equal to its descendant objects. Suppose that we want to add 85 to a max heap in figure 27.1. We first would place the new entry as the next leaf in the tree. Figure 27.2a shows that we add 85 to the left child of the 30. Notice that we actually would place 85 at index 10 of the array in figure 27.1b. So figure 27.2a is no longer a heap since 85 is out of place. To transform the tree into a heap, we let 85 float up to its correct location. Since 85 is larger than its parent, 30, we swap it with the parent as figure 27.2b shows. The 85 is still larger than its new parent 80, so we swap it again, figure 27.2c. Now 85 is less than its parent, so we have transformed the tree in figure 27a into a max heap. What about avoiding swaps? Although the swaps mentioned in the previous segment make the algorithm easier to understand and to describe, they require more work than is actually necessary. Instead of placing a new entry in the next available position with the tree, as we did in figure 27.2a, we need only reserve space for it. In an array-based implementation, we simply check that the array is not full. Figure 27.3a shows that the new child as the empty circle. We then compare the new entries, the 85 in this example, with the parent of the new child. Since 85 is larger than 30, we move the 30 to the new child as figure 27.3b shows. We treat the node that originally contained 30 as if it were empty. We now compare 85 with the parent 80 of the empty node. Since 85 is larger than 80, we move the 80 to the empty node, as figure 27.3c shows. Since 85 is not larger than the next parent 90, we place the new entry into the empty node, as figure 27.3d shows. Figure 27.4 shows these same steps for from the viewpoint of the array that represent the heap. Part A, which is analogous to 27.3a, we note that we have room for a new entry at index 10. The parent of this location is at location 10.2 or 5, 10 divided by 2 or 5. We thus compare the new entry 85 to 30, the content of the location at index 5. Since 85 is greater than 30, we move 30 to the location at index 10. Figures 27.4b and 27.3b. The remaining steps proceed in a similar fashion. Note that figure 27.4d corresponds to figure 27.3c and figure 27.4f corresponds to figure 27.3d. So figure 27.4 shows these same steps from the viewpoint of the array that represents a heap. In part A, which is analogous to figure 27.3a, we note that we have room for a new entry at index 10. The parent of this location is at location 10 divided by 2 or 5. We thus compare the new entry 85 to 30, the contents of the location at index 5, and so forth. And so we're just continuing this on, which we just talked about in the last chart. What about adding an entry? Let's redefine the algorithm. The following algorithm summarizes the steps that add a new entry to a heap. To ignore the first location of the array, we simply ensure that the parent index is greater than 0. Notice that the size of the array is expanded as necessary after the addition, as we did for A-list add method in chapter 11. For the method add, we now closely follow the previous algorithm to implement the method add. For removing the root, the basic algorithm, the remove max method for a max heap removes and returns a heap's largest objects. This object is the root of the max heap. Let's remove the entry in the root of the heap in figure 27.3d. Figure 27.5a, as we're showing here, shows the heap as if the root was empty. So for transforming a semi-heap into a heap, the tree in figure 27.5b is called a semi-heap, except for the root, the object and a semi-heap are ordered as they are in a heap. In removing the root of the heap, we form a semi-heap and then transform it back into a heap. As in the method add, we can save time by not swapping entries. Figure 27.6 that we're showing here shows the semi-heap from figures 27.5a and the steps that transform it into a heap without the swaps. The following algorithm transforms a semi-heap to a heap. To make the algorithm more general, we assume that the root of the semi-heap is at a given index instead of at index 1. So in the worst case, the method reheap follows a path from the root to a leaf. The number of nodes along this path is less than or equal to the height h of the heap. Thus, reheap is big O notation h. Recall that height of a complete n node tree is log 2 of n plus 1, rounded up to reheap is a big O notation log n operation. For the method remove max, the method remove max replaces the heap root with the last leaf to form a semi-heap. Like the one in figure 27.6a, the method then calls reheap to transform the semi-heap back into a heap. Thus, remove max has the following implementation. For creating a heap using add, we could create a heap from a collection of objects by using the add method to add each object to an initially empty tree. Figure 27.7 that we're showing here shows the steps that this approach would take to add 20, 40, 30, 10, 90, and 70 to a heap. Since add is a big O notation at log n operation, creating the heap in this manner would be big O notation n times log n. For using reheap, a more efficient way to create a heap using the method reheap, we begin by placing the entries for the heap into an array beginning at index 1. Figure 27.8a provides an example of such an array. Figure 27.8a provides this array can represent the complete tree shown in figure 27.8b. Does the tree contain any semi-heaps that we can transform into heaps? The leaves are semi-heaps, but they are also heaps. Thus, we can ignore the entries 70, 90, and 10. These entries are at the end of the array. Here is another constructor. We can use the technique described in segment 27.14 to implement another constructor for the class max heap. Suppose that n entries for our heap are given in an array of exactly n locations. The following constructor takes this array, copies it into the data field heap, and uses reheap to create a heap. Although the entries in the heap array begin at index 0, we place them into the array heap beginning at index 1. Note that this constructor calls max heap's second constructor, thereby verifying the required capacity and allocating the array heap. So for a heap sort, we can use a heap to sort an array. If we place the array items into a max heap and then remove them one at a time, we will get the items in descending order. We saw in segment 27.13 and 27.14 that using reheap instead of add is a more efficient way to create a heap from an array of items. In fact, we wrote a constructor in the previous segment that invokes reheap for this purpose. So if my array is the array of items, strings, for example, we could use this constructor to create the max heap as follows. Max heap interface string my heap equals new max heap my array. As we remove the items from my heap, we could place them in order back into my array. The problem with this approach is the additional memory required, since the heap uses an array besides the given array. However, by mimicking the heap's array-based implementation, we can make this approach more efficient without using the class max heap. The resulting algorithm is called a heap sort. To create an initial heap from the given array, we call reheap repeatedly, as we did in the constructor given in segment 2716. Parts A and B of figure 27.9 shows an array and the heap that results after this step. Since the array to be sorted begins at index 0, but in the constructor the heap begins at index 1, we must adjust reheap, as we'll see. The largest item in the array of figure 27.9b is now first in the array, so we swap it with the last item in the array, as figure 27.9c shows. The array is now partitioned into a tree region and a sorted region. Following this swap, we call reheap on the top on the tree portion, transforming it into a heap, and perform another swap, as figure 27.9d and 27.9e illustrate. We repeat these operations until the tree region can consist of one item, figure 27.9k. The array is now sorted into ascending order. Notice that the array actually is sorted in figure 27.9g, but the algorithm does not detect this fact. So here, let's do some adjusting of the reheap. We must now revise the method reheap so that it is suitable for our sorting algorithm. The method in segment 2711 uses the data fields heap and last index of the class max heap. Here we make them parameters of the method. Thus, we change the method's header as follows, and you can see that in the listing. And then just to finish up here, so the method heap sort, the implementation of heap sort begins by calling reheap repeatedly, as we did in the constructor given in segment 2716. To create an initial heap from the given array, however, since the heap begins at index 0 instead of 1, we must adjust the loop somewhat. This loop assumes n entries in the array heap beginning at index 0. Exercise 3 at the end of this chapter asks you to verify the starting value of root index, and you can look at that if you'd like. So like merge sort and quick sort, heap sort is a big O n log n algorithm. As implemented here, heap sort does not require a second array, but merge sort does. Recall from chapter 16 that quick sort is a big O notation n log n most of the time, but is big O n squared in the worst case. Since we usually can avoid quick sort's worst case by choosing appropriate pivot, it generally is the preferred sorting method. Okay, well, that'll end our lecture for now. Thank you very much.